Hello everybody, welcome back. So this is the start of section 2.1 from my proofs book. And in the last video, we discussed the importance of definitions and how in math definitions offer precision. We're very precise with our definitions, and that's good. In everyday language, people are not as precise, and usually that's perfectly fine for ordinary conversation. But in math, our language is precise, and that's very important. And having precise language allows us to be very rigorous with our mathematics. Now, I did say that there are a couple things that I'm going to assume we know ahead of time. First, I'm going to assume you know what the integers are. So the integers are 0, 1, 2, 3, 4, etc., and also -1, -2, -3, -4, etc. Okay, so those are the integers, and it is possible to rigorously define the integers, but honestly, it would make you more confused. It would be more confusing than enlightening. So that's not worth it. Another thing, the one extra thing that I'm going to assume, I have written up here, kind of stuck it to the side on my wall here. It says, hopefully that's somewhat readable, it says fact 2.1. It says that the sum, difference, and product of integers is still an integer. So if you add together two integers, you still get an integer back. If you subtract two integers, still get an integer. If you multiply integers, you still get an integer. Okay, notice I didn't say division. It's not true for division, not true for, I don't know, square roots or other things. But it is true for the first three basic arithmetic operations: adding, subtracting, multiplying. Okay. Also, in that fact is one more statement. Also, every integer is either even or odd. Okay, so I'm going to assume that. It's not a lot. Hopefully it makes a lot of intuitive sense to you. But I will assume that as we move forward. Okay, but I'm not assuming much else. For example, I'm not assuming we know the definition. We know what an even number is or an odd number is. We should define it. Now, intuitively, you know that like 2, 4, 6, 8, 10, at least those are even. And maybe the negatives too, maybe 0. And the odd numbers are the other ones, 1, 3, 5, 7. So you have to think about it, right? So what should the definition be? Well, I could say something like that. It's numbers which fit the pattern 2, 4, 6, 8. You keep adding 2 every time. But that's not a good definition because it's hard to work with that definition. And we're going to want to be working with our definitions. They're going to appear in our proofs. And therefore, we want a good definition for when we have to use it. So think to yourself, how would you define, given what we just discussed, how would you define an even number? Many options. You might have said a number that's divisible by 2. That's a pretty good definition. And our definition will be similar to that. But saying something's divisible by 2 sort of says that in order to know it's even, you kind of have to check a property. Like you have to take it, divide by 2, see if you get an integer back. It's not quite as easy to work with as saying a number is even if it is 2 times some other integer. It's the same definition, but this way, say a number is even, an integer n, I should have said, an integer n is even, and usually you underline the word that you're defining, is even if n equals 2k. Okay, so if n is twice an integer, and k has to be an integer, k can't be 2.5 or pi or something. No, if n equals 2k for some integer k. All right. So what would be an odd integer? How would you define that? Maybe n equals 2k plus 1. That's pretty good. Again, it gives you sort of an equation that you can work with. So if you're given an even integer, you can sort of substitute in a 2k. That's nice. That's a good. And now you just have 2 other integers that you're working with. That's really good. So let's do the same thing for odd. An integer n is odd if n equals 2k plus 1 for some integer k. Does that make sense? You could say an integer is odd if it's one more than an even integer. But again, it's harder to use that. Then you have to then appeal back to, well, okay, well now what is an even integer? Writing it like this as an equation will be really nice, as you'll see in a second. In a second, we're going to prove something, and you'll see how it comes into play. But first, let's go ahead and write down a few examples. So I'll use e.g. for example. It's a Latin thing. There are a few of these Latin abbreviations which are used very often in math, especially for board work. E.g. means example. I.e. means like in other words. I should have thought about this ahead of time. What else? Those are the main ones. Some people use like viz, V-I-Z. I feel like there's one that I'm missing off the top of my head. But e.g. and I.e., I think those are the two biggest ones. Okay, so e.g., so if, for example, 6 is even or odd? Even. 6 is even because, why? Well, because does it satisfy the definition, right? You always should go back to the definition. So 6 is even because 6 equals 2 times 3, and 3 is an integer. I should do int period for integer. Again, good for board work, not good for your solutions on homeworks. Okay, so 6 is even. 9 is odd. Because, why don't you write it out? Because it satisfies the definition. Because 9 equals 2 times 4 plus 1. And 4 is an integer. What about 0? Does 0 count as an integer? Yeah, it's definitely an integer. It's in the list of integers. Does it count? Is it an even number? Is it an odd number? Is it neither? What do you think? Well, we don't have to ask the question. We just look at the definition, right? This is no longer an opinion thing. Like, do you think 0 should be considered even or odd or neither? No, it's not an opinion anymore. Does it satisfy the definition or does it not satisfy the definition? So 0 is even because it satisfies the definition. Because 0 equals 2 times which integer? 0. 2 times 0. And 0 is an integer. Okay. So you see, that's the good thing about definitions in math. They remove ambiguity. There's no longer a question of what's your view on the matter. Before the definition is created, you have a view on the matter. But once it's settled and once mathematicians agree that, yes, this is the definition, then you just appeal to the definition to decide these things. You know, and think about an odd number. If I take n equals 2k plus 1, and I switch it to n equals 2k plus 1.000001, I just shift it just slightly, it's no longer odd, right? Again, the lines in math are very sharp. Okay, what about odd numbers? Are odd numbers considered even or odd? Like negative 15? Well, yeah. There's no reason why they can't be, according to the definition. Negative 15 is odd because negative 15 equals 2 times negative 8 plus 1, and negative 8 is an integer. Okay, so there you go. So in math, you can just check the definitions to tell these things. Is that clear on the screen? Yeah, looks clear. Good. Okay. So now that we have a definition of what it means to be even and odd, a very precise definition, now let's start to prove things. So here's the first proposition. And in the book, sum of two evens, this should be 2.4, proposition 2.4. And it says, the sum of two even integers is, what do you think? Is even. The sum of two even integers is even. And probably pretty quickly you can run through your head and check a few in your mind and say, yeah, 2 plus 4 still even, 6 plus negative 2, 16 plus 18, yeah. Seems to be holding true, but let's actually prove it. Now, so when you really go down to the basics, the things that you're proving have to be simpler, right? Because you're assuming very little. We're assuming that we know what integers are, that integers in 3 ways combine to be other integers, they're even or odd, and we have a definition of even and odd, and that's it. So if we're going to prove things, they have to be using only those few basic ideas. So they're going to be simpler. Now, in many ways, that is a good thing, because when you're trying to learn proof writing, well, first of all, there's the writing part of it, so this is good practice. And there's this other skill, which is working with definitions. That's the title of this section. And it's good that the math is simple, so that way you can put all your mind can be focused on actually formulating the proof, using definitions, writing it out nicely. So those are other skills that you sort of reduce the strain on the math part of your brain in order to work out the other parts of your brain. So this is a good thing. All right, so here's the idea behind this proof. The idea is that we're going to start, well, first, we're going to rephrase this proposition. The sum of two even integers is good, but, the definition says an integer n is even if. So if you had a variable that says this represents an even integer, then you have a definition that you can apply in the problem. But without that, it's not quite there yet. But the idea is that this statement is the same as this other statement. So quote, if n and m are both even, then n plus m is even. Do you see how those are both the same thing? And you also see how the second one seems a little bit more easy to work with? The first one wasn't phrased as an if-then statement, and it didn't use variable names, but same thing, and now we have sort of this is what we're assuming, this is what we're trying to prove. We have variable names, so we can apply the definition 2.2. It's nice. Okay. So this is going to be our basic approach. And again, at any point, feel free to pause the video and try this on your own. See if you can work it out and then come back. So here's your basic approach, is that we're going to start by assuming, we're going to say assume that n and m are even. Okay. And then we're going to apply definition 2.2 to say, so because they're even, n is 2 times some integer, and m is 2 times some integer. We can't use k for both of them. It's just a variable name. It doesn't matter what we call it. But we shouldn't use k for both of them because it's not necessarily the same integer in both cases. So I'll just use 2a and 2b. Okay, so we can say, assume they're both even. Okay, then using definition of an even number, so that's definition 2.2. Therefore, we can write them using these, write them in this new way. Therefore, n must be the same thing as 2 times some integer, and m must be 2 times some integer. Okay? And then somehow we have to get down to the point, so ... Somehow we have to reach the point that our goal is to show that n plus m is even. Therefore, n plus m equals 2, maybe I'll use k here. So somehow we have to get down to the point where n plus m is now also 2 times the integer. And therefore, what's our goal to show that n plus m is even? Well, as long as you're 2 times the integer, therefore it's even. Therefore, n plus m is even. So to go from it being 2 times the integer to being even, that is another application of definition 2.2, the definition of being even. So this is the mystery step. This is the step where we have to somehow figure out how to do this. But as long as we can start here, apply the definition, then a mystery occurs, then magic occurs, and then we get down to this point, then we can just apply the definition one more time to get here. Does this make sense? So if we're trying to prove this, this is a way to start here and end there. So how do we do this? What's this mystery step in between? Well, in this case, it's just a little bit of algebra. So go ahead and pause the video, stare at this, make sure this makes sense as a proof outline. And then, where's my rag? I need to wash this. That still works good enough. Let's see here. How much room do I need for this proof? Can I do it here? I can probably do it here. Actually, maybe I'll pause the video now and just write the first step on the board so you're not watching me write. Be right back. All right, so I added definition in 2.2 to this piece of paper over here. So n is even if n equals 2k for an integer k. It's odd if n equals 2k plus 1 for an integer k. All right, and over here, I wrote up the parts of the proof that we already sort of established. The proof's going to start by saying, assume n and m are even by definition 2.2, and you can refer to the actual numbers in your work, or you can just say, by the definition of an even number. Both of those are fine. I wrote, mostly for space, I wrote, by definition 2.2, this means that n equals 2a and m equals 2b for some integers a and b. Okay? Then, this is the question mark, question mark, question mark. Something has to happen here. We still have to figure that out. And the goal, so then what I did is I went to the very bottom of the page. This is actually not a bad proof strategy, by the way. You start at the top, you go at the bottom, you kind of work your way to the middle and see if you can bridge the gap. So what are we aiming to do? We're trying to show that n plus m is even, right? That's the proposition. That if you start with 2 even integers, you end up, and you add them together, you get another even integer. So that's our goal, to show that n plus m is even. So how would we get there? Well, by definition 2.2, this is what we would need to get there. There's a little blank missing here. We'll fill that in a second. But basically, what we want to show is that n plus m equals 2k for an integer k, right? If we can show that, then we get this, and we're done. So do you see how that as long as we can go from this to this, then we're done. So how do we get there? Well, we're trying to get down to n. We're trying to say something about n plus m equaling something. So we have an n equals and an m equals. So why don't we add add those two equations together. Let's add the left sides and add the right sides. Make sense? Essentially, we're taking this equation and we're adding m to both sides. On the left-hand side, we're literally adding m, and on the right-hand side, we're adding something that m is equal to. They're literally the same thing, they're equal, so we can switch it out. That's another way to think about it, in case that's at all confusing. But here you go. So here's an equation. N plus m equals 2a plus 2b. And we're trying to get down to 2 times a single integer k. So do you see how to do that? We don't want like a somewhere, we just want a single 2 times a single integer k. Yeah, so one idea is you could factor out the 2. You see that? And this is great. So we want a single integer, but we have a sum of integers. What tool do we have? We only have a couple tools at this point. So what thing do we have that can tell us that adding 2 integers gives you another integer? Well, that was that fact 2.1. The sum and difference in product. But the first thing is the sum of 2 integers is still an integer. So, so we should say, and since a and b are integers, so is a plus b. And that is according to fact 2.1. Okay, so this is the bridge between our first application of the definition of an even number and our last application of the definition of an even number. Okay, let's quickly go through it one more time to see if you're convinced. Oh, so we have an integer a plus b, but the actual definition has a single integer. So the thing is, just switch it out. It is an integer. So, let's say, so n plus m equals 2 times an integer. We just established that as an integer. So let's just give it a new name. Let's call that integer k. And now we have n plus m equaling 2k. And that's exactly what we want. Does that make sense? So start at the beginning. Let's assume n and m are even. We want to get down to n plus m being even. So step 1, we apply the definition of what it means to be even to both n and m. So apply the definition, n equals 2a, m equals 2b. Next, a little bit of algebra. Add the 2 equations together, factor out a 2. Okay. Next up, notice that a plus b, those are both integers, so their sum, according to fact 2.1, still an integer. So n plus m equals 2 times an integer. Let's give that integer a name. Let's call it k. It's a nice name. It exactly is the variable even that appears in the definition of even. So we have shown that n plus m is equal to 2 times an integer k. And we even know precisely what that k is. It's the a and the b that appeared earlier. But that's an integer. So n plus m equals 2 times the integer. Therefore, by the definition of even, it's even. And we are done. So now we can have the wonderful feeling about putting a square at the end of your work. Not only does this signify the end of your proof, it gives you a little dopamine hit. It's always fun to put that box. So there you go. This is the proof of our first proposition dealing with integers, even numbers. This is a very rigorous proof. I hope you agree with that. So look it over, make sure it makes perfect sense to you. And next, try to prove that the sum of 2 odd integers is, what should it be? Should it be odd or even? Even, right? 3 plus 5, those are both odd. They add up to 8. That's even. So now take a moment and try to prove to yourself that 2 odd integers is even. And have it be a complete, formal, nice-looking proof and it'll look very much like this. A few minor details, but very similar. And come back next time. In the next video, I will show you how to do it. All right, see you then.